Okay, we're picking up where we left off in the previous video, going through this section on the differentiation rules for the trig functions. So not the inverse trig functions. We'll talk about the inverse trig functions later. Just the differentiation rules for the 6 trigonometric functions: sine, cosine, tangent, cosecant, secant, and cotangent. So, but in the previous video, we actually didn't even get into the section. All we talked about was, why was it necessary that we specify that we're clear on what exactly the unit of the input, the unit of the input angle into the trig functions are, before we actually start developing these differentiation rules? So they made it very clear that for everything we're about to do here, the argument of the angle into the trig function is in units of radians. And this is definitely necessary because all of the rules we're about to come up with are only directly applicable if the angle is in radians. It's not that you can't take a derivative of a trig function if the argument is, say, in degrees. It's not a big deal. The idea is you just say, okay, so the argument needs to be in radians. So if the x is in degrees, then you need to convert that to radians. So you've got pi radians for every 180 degrees. So if x is in degrees, you're doing this. You're finding the derivative of this function, which you'll still make use of the derivative rules for the trig functions we're about to develop, but then you're going to actually get a derivative that's different from if the input was in radians, because you've got this factor here. So how do you take this derivative with this factor in front of the argument? Well, that's what we'll need the chain rule for. But what makes this so confusing is, why are the differentiation rules for the trig functions dependent on units, but everything we've done up to this point, so like the derivative, the power rule for x to the n, we didn't have to make any statement about units. It doesn't seem to be dependent on units. And it's the exact same idea with, we're going to see with the official differentiation rules for the exponentials and logarithms. And so if you've just watched the previous video, the introduction to the differentiation of the trig functions video, where we talk about this, you still might feel a little unsatisfied, like the question hasn't been fully answered. And I understand this is actually a really confusing question to answer, because there's a lot of topics mixed in here. You've got the fact that the trig functions are transcendental functions. So we've got like exponentials, logarithms, and the trig functions are transcendental, but then like x to the power n, as long as n isn't an irrational number, or algebraic functions. So what does all that mean? There's also the question of, so everything we've done up to this point with the derivative, if you think about it, it's all been based on an assumption of we're dealing with a rectangular coordinate system where both the input and the output axes are linearly scaled. So they're not logarithmically scaled, for example. So how do you deal with derivatives if you're in like a polar coordinate system, or if you're still in a rectangular coordinate system, but one or both of the axes have a different scaling? How do all of these differentiation rules we're talking about in this chapter, which are based on the assumption of a rectangular coordinate system with linearly scaled axes, well, how do you adjust these differentiation rules for different types of coordinate systems or different types of axes? So I'm going to plan to make an entirely separate video as soon as I can. And by the time you're watching this video, it might already be uploaded. I'm going to put it right around here in the playlist, either just before this video or maybe just after this video, where we're really going to go into full detail on everything, so we can get a really clear answer on why exactly it seems as though the derivatives of the trig functions are dependent on units, but the derivatives of all of the other functions, even the other transcendental functions of exponentials and logarithms, aren't. Okay, but overall, like the overall general rule for this, even though this might not be very satisfying, is it's really just like the James Stewart says here, the author of this textbook says here, in that, so trig functions are defined. The definition of trig functions is for inputs of angle in radians. It's understood that, so if you have f of x is equal to sine of x, it's understood that sine of x means the sine of the angle whose radian measure is x. And so now you might say, well, yeah, but we can input angles in any unit into a trig function. I mean, we do that on our calculators all the time. We switch to degree mode, and evaluate trig functions in degrees, if you think about the definition of trig functions, the most general definition of trig functions is purely based on angle. It doesn't matter what the units of the angle are. You've got some angle measured from standard position, so it's positive going counterclockwise with the edge number one, straight edge number one being the horizontal x-axis. Then you draw the second edge wherever. I'll put it out here. The length of this edge doesn't matter. So now here's some angle. An angle fundamentally you need two straight sides and a vertex. That's all an angle needs. And an angle is just the measure of this opening span between the two straight sides as one side rotates relative to the other with respect to the vertex. So you've got this angle here. And so for any angle in any of the four quadrants, trig functions are strictly defined, again, just relative to this opening here. It doesn't matter what the units are. If you have any angle in any units, and with this level of opening between the two sides, that's all you need to get values of trig functions. It's just, so you pick any location along this line, it doesn't matter where. You drop a vertical line that's perpendicular to the x-axis. Now, this point here has coordinates x and y, and x and y could be negative based on the point. So x is negative here, y is positive here. Now, the radius here is always positive because of the square root of x squared plus y squared. And so then the trig functions are just, okay, sine of theta is y divided by r. Cosine of theta is x divided by r. And tangent of theta is y divided by x. And then cosecant, secant, and cotangent are just the reciprocals, right? So you can see the trig functions are defined based on any angle in any units. But what they're saying here, what James Stewart is saying here is that, yes, like the trig function, the definition of trig functions is based on any angle, but they're still defined, at least in terms of calculus and math, in the sense that no matter what the angle is, no matter what the units of the angle are, the trig functions are defined so that you're going to convert this angle to radians and then input it into the trig function. So that's why so we're about to come up with a differentiation rule. We're going to start by coming up with the differentiation rule for sine of x. So that's when x is in radians. But if you're going to be inputting an angle in degrees into the sine function, which you're allowed to do, then you need to specify it this way. So this is x in radians, but x in degrees. Well, you need to convert it to radians first. So, right? So you're actually taking the derivative of this function when the input is in degrees. That's the difference. But again, though, I mean, I know personally I didn't find this as the most satisfying answer to this overall question because, I mean, okay, we've got other transcendental functions that require dimensionless inputs, like the logarithm and the exponential. Why isn't it required that we say that, okay, here's this like base unit for log base b of x, and so we've got a differentiation rule for the log base b of x, but if you switch units, then you have to say, okay, log base b of, and then apply the conversion factor. Well, why don't we have to make any statements like this when it comes to the differentiation rules for logarithms and exponentials? So again, I'm going to make it a whole separate video that's really going to break this down. All right. So, but again, like it does say here in all of really mathematics in general, when you're dealing with trig functions, it's understood that the trig functions are defined with the input units into the trig function being in radians. Now, you can still evaluate trig functions in terms of angles in whatever units you want. You just need to convert that to radians first and then input it into the trig function. Okay, so a similar convention holds for the other trig functions: cosine, tangent, cosecant, secant, and cotangent. Recall from section 2.5 that all of the trigonometric functions are continuous at every number in their domains. Yeah, so remember, all of the core function types that we've learned in algebra and trigonometry, they're all continuous everywhere in their domains. They're not continuous everywhere. Not all, like polynomials are continuous actually everywhere from negative infinity to infinity, but other functions aren't continuous everywhere. Like rational functions, you can't divide by zero, but if the function exists at a point, So that point is in the domain of the function, then the function is continuous. That's a property of all of the trig functions and all the functions we learned in algebra. And so sometimes this isn't the case, right? You could have a jump discontinuity. So the function is defined here. This point is within the domain of the function, this point A, but it's not continuous here. So just recall that the trig functions are continuous at every number in their domains. And so it says if we sketch the graph of sine of x and use the interpretation of f prime of x as the slope of the tangent to the sine curve in order to sketch the graph of f prime. Yeah, so just like we did in the introduction to the derivative as a function section, we started off by, we were given a function and then we sketched the derivative based on our understanding of what the derivative means as the slope of the tangent line to a point. So they're saying, let's go ahead and try and do that here for sine of x. So here's sine of x. And so we can first look for horizontal tangent points. So you've got horizontal tangents, which we know on the derivative graph are going to be x-intercepts. Okay, so they plot some x-intercepts. All right, then we can see that. So if we come here, the slope is 0, we have an x-intercept. As we continue forward, the slope is increasing. It's getting more positive. So we know the derivative graph is going to come above the x-axis. But then at some point, it's going to get more positive, but we know it's going to turn back and go back towards 0 because we're going to get to another horizontal tangent, right? So the derivative it's increasing. It's getting more positive, but we know it's going to turn around and come back to 0. So you're getting a more and more positive slope, but then it looks like at the x-axis here, instead of the derivative increasing, getting more positive, it turns around and starts coming back to 0. And so what we do is, so it's going to turn around here, and so we just draw this like smooth curve. The slope's getting more positive, but then it eventually starts to, instead of getting more positive, it starts to turn around and go back to 0 to where now it's back at 0. But it just continues through past a slope of 0 to a more negative slope. So it's getting more and more negative until it eventually stops, turns around, and goes back towards 0 again. So it's getting more and more negative, then it stops, turns around, and goes back towards 0 again. And so what we see here is it looks as if what we've just sketched as the derivative of sine of x is the curve cosine x, right? This is just you've shifted sine of x to the left pi over 2. Cosine starts at 1. And so, okay, let's try and get an official formula using the definition of the derivative for the derivative of sine of x. So you've got f of x is equal to sine of x, and we're thinking that f prime of x is going to be cosine of x, but let's see. So, okay, f prime of x is the limit as h approaches 0 of f of x plus h minus f of x all over h. So you have sine of x plus h minus sine of x all over h. So they use you have the sum and difference identities, trig identities that you can use to break up sine of x plus h. That's what they do. And they break this up into two separate fractions. Then they pull out this sine of x here and this cosine of x here. Then they apply you have the sum rule for limits. Remember, limits are really flexible. And then you could also then apply the product rule you can break up, use the sum rule to apply the limit to each of these, but then you can apply the limit to just sine of x and this, and just cosine of x and this. And so now it says 2 of these 4 limits are easy to evaluate because sine of x is not a function of h. As h changes, sine of x doesn't change. So sine of x is just a constant. Same with cosine of x. So these 2 limits, this limit is just sine of x, and this limit is cosine of x. So now we just need to evaluate these 2 limits. You have the limit as h approaches 0 of cosine of h minus 1 over h, and the limit as h approaches 0 of sine of h over h. If we can get these 2 limits, then we've got the full general derivative for sine of x, like in general. Okay, so this limit here was a limit that we talked about in chapter 2, and we were told that this limit is equal to 1, but that they were going to prove it later, and that's what they're going to do here. They're going to prove it. So we can just change h to theta because it's just a variable. So the limit as theta approaches 0 is sine of theta over theta. So this way we can think of theta as an angle in relation to the input into sine. So, okay, they're going to use a geometric argument to prove this limit. And so it says, assume first that theta is an angle that lies between, we know theta is an angle because it's an input into sine, right? And it's in radians. That's necessary for this proof. That this limit doesn't work if theta isn't in radians. It wouldn't be equal to 1. I mean, you could still do if theta was in degrees, you could still do the limit, but it's not going to be equal to 1. Okay, assume first that theta lies between 0 and pi over 2. Okay, figure 2a shows a sector of a circle with center at O. So you have this sector of this circle, AB, with center at O. And there's theta between 0 and pi over 2. And this circle has radius 1, all right? Now, BC is drawn perpendicular to OA, okay? By the definition of radian measure, we have the arc length of AB is equal to theta. Yep. Also, the length of BC is equal to the length of OB times sine of theta. Yeah. From the diagram, we see that. So the length of BC is less than the length of AB because BC is the leg of a right triangle in which AB is the hypotenuse. And also the length of AB is less than the arc length of AB. The length of segment AB is less than the arc length of the length of arc AB. Okay, so therefore, so the length of BC is sine theta because OB is 1. The length of BC is equal to the length of OB times sine theta, but OB has length 1. So the length of BC is equal to sine theta. So you have sine theta is less than the length of arc AB, which is just theta. So if you divide both sides by theta, which you can do because since theta is always positive between 0 and pi over 2, you're not going to have to flip the inequality. So you get sine of theta over theta is less than 1. Okay. Now it says, let the tangent lines at A and B intersect at E. So you have these tangent lines to the circle at points A and B intersect at E. It says, you can see from figure 2b that the circumference of a circle is smaller than the length of a circumscribed polygon. And so what they're saying is that it's obvious that the length of arc AB is less than the length of BE plus the length of AB. Or the length of, what would I say? The length of arc AB is less than the length of BE plus the length of EA. All right. So thus, theta is, which is equal to the arc AB, is less than the length of AE plus the length of EB. And EB we can change to ED because we know that as far as this inequality will still be satisfied because we know that ED is going to be greater than EB for sure. So this inequality will hold because ED is the hypotenuse of a right triangle of which EB is a leg. Okay. Now, but AE plus ED is a leg of this large right triangle. So AE plus ED is AD, and AD is OA tangent theta, but OA is 1. That's the radius of the circle. So what you get is that theta is less than tangent theta. So it says that in Appendix F, the inequality theta is less than or equal to tangent theta is proved directly from the definition of the length of an arc without resorting to geometric intuition as we did here. Okay. All right. So therefore we've got theta is less than tangent theta. So theta is less than sine theta over cosine theta. Okay. Now, so you can multiply both sides by cosine theta and divide both sides by theta. And we can do that because since theta is between 0 and pi over 2, cosine theta is always positive and theta is always positive. So we don't have to worry about flipping the inequalities or anything. Now, but you know that cosine theta is always less than 1 if cosine theta is in general less than or equal to 1, but if theta is not, it can't be equal to 0 or pi over 2, it's just between 0 and pi over 2, then it's less than 1. Same idea with sine theta, but if you're always dividing sine theta by a positive number, then this is going to be less than 1 as well. Sine is actually always positive in quadrant 1 as well. Okay, so we know that the limit as theta approaches 0 of 1 is 1, and the limit as theta approaches 0 of cosine theta is 1. So by the squeeze theorem, we have the limit as theta approaches 0 from the right of sine of theta over theta is equal to 1. So we have to just state that we're approaching from the right because theta is between 0 and pi over 2. But it doesn't matter that if theta, we don't have to state that theta be equal to 0 because with limits, it doesn't matter what the function is doing at the limit point, right? Okay, but the function sine of theta over theta is an even function. So its right and left limits must be equal. So therefore, we can just go ahead and update this to the limit as theta approaches 0 in general of sine of theta over theta is equal to 1. And there we go. That is exactly what we're trying to prove. This is the limit we need. So this, at limit as h approaches 0 in general of sine of h over h is equal to 1. Okay, now we just have this last limit here. So the limit as theta approaches 0 of cosine theta minus 1 over theta, they simplify the limit function. They multiply by the 1 in the form of the conjugate of the numerator. So now you get this limit function here. So cosine squared theta minus 1 using sine squared plus cosine squared is equal to 1. You can convert that into minus sine squared theta. Then you can break this up into two separate functions being multiplied here, and then using the product rule of limits, break this up into two separate limits. Now this limit is equal to 1, and this limit you could just do a direct plug-in. And so you get that the limit as theta approaches 0 of cosine theta minus 1 over theta is equal to 0. And so there we go. This is 0. So you're left with f prime of x is equal to cosine of x. And there's the proof. That's what we suspected based on just doing the diagram or just drawing the derivative by hand, and that turned out to be exactly the case. So there is the differentiation rule for sine of x, assuming x is in radians. Really simple. The derivative of sine of x is just equal to cosine of x. All right. What is the derivative of, practice problem here, differentiate y is equal to x squared sine of x. So we could just use the product rule. Derivative of the first times the second plus derivative of the second is just cosine of x times the first. There you go. Okay, so using the same methods as what we just did, going through the whole limit definition, it can be proved that the derivative of cosine of x is minus sine of x. And so now with the derivative of sine of x and cosine of x, we can get the derivative of tangent x by just putting tangent in the form of sine of x over cosine of x and using the quotient rule, right? The derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared. And that's what they do. And get that the derivative of tangent of x is equal to secant squared of x. And so it says the derivatives of the remaining trig functions, cosecant, secant, and cotangent, can also be found easily using the quotient rule. So we collect all of the differentiation formulas for the six trig functions in the following table. And just remember that they're only valid when x is measured in radians. So there's the differentiation rules for the six trig functions. Okay. So it says here, let's differentiate this function. And then for what values of x does the graph of f have a horizontal tangent? So just use the quotient rule, the derivative of the top, secant x times the bottom minus the derivative of the bottom times the top. We can just use the differentiation table for the trig functions that we just looked at. to get all these derivatives. And so here's f prime of x. Now, where does the graph of the original function have horizontal tangents? Well, it's just where the derivative, for what values of x does the derivative equal 0? And that's going to be where anywhere where the numerator equals 0, as long as at that same input spot, the denominator doesn't also equal 0. And so you're just saying here you've got these two factors. So where does secant x equal 0? And where does tangent x minus 1 equal 0? Where does tangent x equal 1? So secant x is never 0. And right, if you remember, the domains are the ranges of secant and cosecant, like they go from 1 to infinity and then from minus 1 to infinity. Okay, but tangent of x is equal to 1 at all of these locations when n is an integer. And so you can see where you've got these horizontal tangents. Those are some of these x values. You've got the slope of the original function is equal to 0. Here, here, and here. Okay, trig functions are often used in modeling real-world phenomena. In particular, vibrations, waves, elastic motions, and other quantities that vary in a periodic manner can be described using trig functions. In the following example, we discuss an instance of simple harmonic motion. Yeah, so okay, an object at the end of a vertical spring is stretched 4 centimeters beyond its rest position and released at time t is equal to 0. And so its position at time t is, which you could get this from, so it's a simple system in which, so this is a frictionless spring. So you're going to pull it 4 centimeters beyond the unstretched length of the spring, but then you pull it to 4 centimeters and then you release. And if there's no friction, it's going to oscillate forever at the same amplitude. It's going to go from +4 to -4. Now you might say, well, that's not realistic, right? There's friction everywhere. This is going to damp out. So this isn't a realistic model. That's true, but one thing that I learned is that the realistic models are just built upon these foundational models. So it's not like you're going to model a real system with friction. You're going to do something totally different. No, you're going to add damping terms onto the frictionless model. So this is like the foundation. So, but okay, you would find a formula like this starting with Newton's second law of motion. So the force F is equal to ma. You know the mass of the spring, or the mass of the block. You assume the spring is effectively massless. So you know the mass of the block. You know the force from the spring. So you can solve for the acceleration, and then you use integrals to get a displacement function like this. So, okay, but if this is the position as a function of time, so when time t is equal to 0, cosine of 0 is 1, so you're at 4, +4. And then you release the block and the timer starts. And so here's the position as a function of time. It's 4 cosine t. So since cosine t goes from -1 to 1, you're just oscillating between 4 and -4. So now it's asking what are the velocity and the acceleration as a function of time. So we know that s prime is the velocity. And so here that's just going to be the derivative of cosine is minus sine. So -4 sine of t. And then s double prime is the acceleration. And so you just take the derivative of s prime. So that's the derivative of sine is cosine, so -4 cosine t. And so what they do is they plot, here's the position, here's the velocity, here's the acceleration, just these 3 sinusoids, right? With the same amplitude, but they're just shifted relative to one another. And the idea is, so you pull the block to 4 centimeters, right at the instant you release the block, the acceleration is like right at time 0, right? Like the instantaneous moment in nanoseconds, even shorter than nanoseconds. If you release that block, the acceleration is maximum and it's in the negative direction. The velocity is increasing in this direction. This is positive s going down. the block is accelerating even though it's not moving. Right when you release the block, the velocity is 0. It's not moving. It's still accelerating though in the negative direction. The position is at +4. So it's accelerating, its velocity is increasing, right? All the way until you get to the equilibrium position, in which case there's no force on the block, so there's no acceleration, but it's traveling at its max speed. Then as you go past equilibrium, the spring force starts pushing in the other direction, in the positive S direction. So, but the block is still moving. It still has a velocity in the negative S direction, but now it's being pushed in the other direction. So it's slowing down. That's why it's slowing down, because it's accelerating in the opposite direction of which it's moving. So it's slowing down, slowing down, slowing down. The spring is getting pushed in more and more and more. It's a higher and higher force. So the acceleration is increasing. It's a larger force. That spring force is increasing until it gets to -4. Now it's motionless, but it's being pushed at the maximum in the other direction. It's accelerating at its max level in the positive direction. A is positive. That's why the velocity it's getting pushed towards the positive velocity. See, so it's pretty interesting. Okay. Now it says find the 27th derivative of cosine of x. So here they're just trying to point out it's like the indestructibility of, as far as differentiating the trig function. So if you noticed, when it comes to, if we take the derivative of like a polynomial, x cubed, and we keep taking consecutive derivatives, the second, third, fourth, eventually this gets like destructed to where the derivative will go to 0. So the 27th derivative of x cubed, if this is f of x, is going to be 0. But functions like the trig functions are unique. So to figure out the 27th derivative of cosine of x, so okay, f of x is equal to cosine of x, f prime of x is minus sine of x, f double prime of x is, so the derivative of sine of x is cosine of x, just positive cosine of x, so f double prime is minus cosine of x, f triple prime is, so the derivative of cosine of x is minus sine of x, so minus times minus, f triple prime is sine of x, the fourth derivative is cosine of x, and so now we're back at where we started. Now we're back to cosine of x. So the derivative of the fifth derivative is just, okay, we start the pattern all over again. So there's a cycle here of length 4. Once you get to like every fourth derivative, you're going to be back at cosine of x. So all we need to do is say that, okay, so 6 times 4 is 24. So the 24th derivative of cosine of x is cosine of x. So the 25th derivative is minus sine of x. The 26th derivative is minus cosine of x. And the 27th derivative is sine of x. Okay, so now it says our main use for the limit in equation 2. So the limit as theta approaches 0 of sine theta over theta is equal to 1 has been to prove the differentiation formula for the sine function. Yeah, we really needed this limit to get that official proof of the fact that the derivative of sine theta is equal to cosine theta. But this limit is also useful in finding certain other trigonometric limits, as the following 2 examples show. So yeah, we're just going to want to keep this limit in mind. We'll have to use this limit for other problems. So what is the limit of, let's see, the limit as x approaches 0 of sine of 7x over 4x? Well, what they do is if we can manipulate this function to get to where it's sine of 7x over 7x, which we can do by, so if we take out a 7/4, so we've taken out the 1/4, but now we need to, because we just brought this 7 out of nowhere, we need to add a 7 in the denominator. So we just multiplied by 7 over 7. and then took out the 1/4. All right, so now we're going to make a substitution that u is equal to 7x. So what we've got is 7/4, and then the limit function changes to sine of u over u. But okay, but what does u approach now once we make this substitution? So we figure this out by saying that, okay, as x approaches 0, what does u approach? Well, u also approaches 0. You have to check that. It's not always the case that when you do a substitution and a limit, that the limit point doesn't potentially change. But in this case, it doesn't. So we're just left with the limit as u approaches 0, sine of u over u. Well, that's just 1. So this limit is equal to 7/4. Okay. Now, what is the limit as x approaches 0 of x times cotangent of x? So we could potentially just apply the product rule of limits, separate this up into two separate limits, but the limit as x approaches 0 of cotangent of x doesn't exist, which, remember, the general limit laws, that the sum and difference law, the product rule for limits, etc., aren't valid if any of the limits don't exist. And really what that means is that you can't say that, so as x approaches 0, x goes to 0, and this is undefined. So, that must mean that the entire limit doesn't exist. Not necessarily. You can't make, if either, when applying most of those limit laws, if either of the limits you break up the limit into don't exist, then you can't make any statement. The limit law effectively doesn't tell you anything. You have to go another route. So that's what they do. So we need to manipulate the limit function. So they change cotangent into cosine over sine. Then they bring the x into the denominator. So sine of x, cosine of x over sine of x divided by x is the same as this here, right? Now we can apply the quotient rule for limits, and you're going to get this limit exists. This limit is equal to 1, but now we know this limit as well. This is 1. So the entire limit is equal to 1.